Hi everybody, it's Christina here, and today we're going to talk about the resting membrane potential and how that works and why you would want to have one. So let's label our field up here, resting membrane potential. Okay, so before we go into drawing out the how and what and why of the resting membrane potential, we need to establish what kinds of cells have a resting membrane potential and why we would want to have one at all. So the kinds of cells that make use of a resting membrane potential the most are what we call the excitable cells. And excitable cells are cells like neurons and like muscle cells. So excitable cells like neurons and muscle cells are cells that respond electrically and chemically to stimuli. That's a terrible C. Electrical. Respond with electrical excitation. So when we talk about the resting membrane potential, what we're talking about is a deviation from a resting state. If the cell is excited, it can respond with electrical excitation. So in my class, the classes that I'm producing this video for in 231 and in 121, we have just begun to talk about the neuromuscular junction and how you excite the sarcolemma of a skeletal muscle cell. But I like to draw out on the board what excitation actually means in the context of a cell membrane first, because it's really hard to talk about how one cell might excite another if you don't really understand what's going on with the membrane. So that's what this video is designed to do. So let's get to business. I'm going to erase these. And I'm going to start drawing. All right, so for a resting membrane potential to exist, we first need a membrane. And remember that these are phospholipid bilayers, so the stuff on the outside and the inside of the cell is water, which means we've got hydrophilic heads. And I'm going to draw my membrane as just being two blue lines representing the hydrophilic heads of the phospholipids. And then in the center of those, I'm going to just make yellow hash marks to denote that this zone is hydrophobic. Okay, so now let's label our imaginary cell according to which side of the membrane is inside and which side is outside. So let's say this is extracellular, and this side is intracellular. Okay, great. So a membrane at rest maintains an electrochemical gradient across it. So electrochemical, let's write that down, is a word that describes a gradient that is a gradient both on the basis of charge, so plus or minus, and chemicals. which include ions, salts, and solutes, etc. So an electrochemical gradient is a case where there are differing amounts of both charge and chemicals across a phospholipid bilayer. So what I'm going to do now is draw myself a bunch of different units of charge on each side of the membrane. So we're going to set up an electrical gradient first. So let's say I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units of positive charge on the outside, and only 1, 2, 3, 4, 5, 6 units of positive charge on the inside. So if we know that thermodynamics tells us that things want to flow down their concentration gradients from an area of high concentration, which in this case is the extracellular side, to an area of low concentration, which in this case is the intracellular side, what that means is that these units of positive charge are going to want to go from out to in. But they can't because my membrane at this stage doesn't include any ion or charge channels of any kind, so nothing can get through. I've made an impermeable membrane for now. So let's address the chemical side of this equation. So what if I tell you that of these positive charges, some of them are sodium, which remember is Na+, so I'm just adding the element sodium to be associated with this positive charge. And a couple of these are sodium too. Actually, I changed my mind. Not that one. All right, so some of my positive charges are actually coming in the form of a sodium cation. Others are coming in the form of a potassium cation. So remember that ions flow down their respective concentration gradients regardless of what any other ion is doing. So if we count our potassiums, 1, 2, 3, 4, only 1, 2, 3 out here, potassium is going to want to flow this direction down its concentration gradient from where there are more potassiums to where there are fewer potassiums. And the opposite is going to be true for sodium. So we have more sodiums out here and fewer in here, so sodium is going to want to flow down this way. So when we have an electrochemical gradient, what we're really saying is we have a gradient where there's charge separation across a membrane, and that charge happens to come in the form of chemicals, in this case, cations. So the arrows here are showing you which way things of the same color want to flow. So positive charge wants to enter the cell, sodium wants to enter the cell, and potassium wants to leave the cell, all based on their respective gradients. So now I've set up a resting membrane potential, which means that I've created a scenario where there are differing amounts of charged particles on either side of a membrane, and those charged particles want to flow in one direction or another. So the membrane is not at equilibrium with respect to either charge or chemicals. Let's add that. Not at equilibrium. Either electrical equilibrium or chemical equilibrium. So I'm going to blow this up and do some more drawing. Bam. Okay, so that's how electrochemical gradients look when they're set up. So the other question we got to ask ourselves is, why have one? The answer is best analogized by thinking about a hydroelectric dam. So I'm going to clumsily draw one down here for you while I talk. So I'm going to pick this. So the principle of a hydroelectric dam is you have a big wall. And behind the wall, you've put a bunch of water. And on the other side of the wall, downhill, you have a lot less water. So based on thermodynamics, we know that the water wants to go from side A to side B, but it can't because we've put a wall in the way. So the kind of energy that we're looking at, if we just hold the water back from flowing to where it wants to go, is potential energy. Which means energy that we have stored up and could be using but aren't presently. However, that's not how dams work. So a dam isn't simply a wall that holds water. A dam is a wall that holds water and lets the water flow through in a controlled way. So in our case, if we're trying to generate power, a hydroelectric dam is going to let a small amount of water through at a time. And because water wants to go from side A to B, if we give it an opportunity, it will. But as it does so, it has to go past a turbine, which spins around as water flows through. The water is going to naturally tend to do this, and that's going to cause the turbine to rotate. So that's how we turn potential energy into rotational energy, which we then use magnets to transform into electricity. Hooray! So you can think of a membrane with a resting membrane potential as having the same principle. If you put one thing on one side of a membrane in greater amounts than another, that thing can flow down its concentration gradient, and you can use that potential energy to do some kind of work. So, returning to our membrane kinetics, now that I've established the what and the why, let's start to address the how. So, how to set up an RMP, resting membrane potential, to begin with. So I'm going to draw my phospholipid bilayer again. And in the middle, I'm going to draw myself, let's make it pinkish red. There we go, a pump. And remember, this area is hydrophobic, so fat-based, and the blue areas of the membrane are water-based, which is why I've colored them blue. We're also going to make the same designation. This side is extracellular, and this side down here is intracellular. Okay, so that begs the question, what is this guy? This is our friend, the sodium potassium ATP ACE. So ATPase means this is an enzyme that is capable of cleaving ATP. So here's how this works. One ATP, let's make ATP lime, is turned into ADP, and inorganic phosphate, which we're going to call PI, releasing a burst of energy. So in this case, the potential energy was stored in the ATP. Now we've released it by cleaving it, and we have a burst of energy that we can use to do work. In the case of the sodium-potassium ATPase, every time it spends an ATP, it's going to kick out 3 sodium, and it's going to let in 2 potassium. So every time this pump acts, it cleaves an ATP, eliminates 3 sodium from the inside of the cell, and allows 2 potassium to enter the cell. The reason it needs ATP is because the cell is transporting sodium and potassium against their concentration gradients. So there's already a lot of sodium out here, and the cell is putting even more out. And there's already a lot of potassium in here, but the cell is putting even more in. So what happens when you do this is that a charge separation builds up. Because remember, if you have water behind a dam, the water is going to push up against the wall of the dam because it wants to flow down. So if you have a lot of positive charge on the outside of the cell, that positive charge is going to line up right next to the membrane because it really wants to flow down. There's still positive charge in here, there's just a lot less of it. So now we have lots and lots of sodium out here and lots of potassium in here. So let's draw those as well. So I'm just going to give myself a lot of potassiums. And in here, I'm going to give myself a lot of sodiums because this cell has been actively pumping them out using ATP. Now this isn't 100% efficient, so let's say that there's at least a couple sodium in here kicking around that have yet to be collected. And perhaps there's a few potassium out here that have yet to be collected and added to the cell. So the sodium-potassium ATPase is also called the sodium-potassium pump. And in a cell that's at rest, this pump is constantly working. And it's not the case that there's only one of these per cell either. You have millions of these little pumps in every cell membrane of an excitable cell that are constantly working, cleaving ATP and exchanging ions to make sure that the membrane always looks something like this when it's at rest. So there's always going to be more sodium outside, less inside, and more potassium inside, less outside. And as a consequence, the outside of the cell is going to have a lot more positive charge than the inside of the cell does. So it's correct to say that the sodium-potassium ATPase maintains the resting membrane potential. And you can actually measure this using some instrumentation that's very delicate, so I'll show you what that looks like. I'm going to draw myself a cell. Just for the sake of argument, I'm making it round. It doesn't have to be round. It could be long and skinny like a neuron or like a skeletal muscle cell. And we know that there's a lot less positive charge inside than outside, but we want to know exactly what the difference is. So if I take a glass needle and I touch the tip of it to this little patch of membrane right here, I can measure the difference in ions between the extracellular fluid, which is inside of this glass needle, and the inside of the cell itself. So this measures the difference. And that difference is expressed in millivolts, which is 1,000th of a volt. So very tiny amounts of electricity. So an average excitable cell has a resting membrane potential of about negative 70 millivolts, which means it's 70 millivolts more negative inside than it is outside. Or if you were to subtract the charge difference, there would be a difference of negative 70. If you undo this negative 70 by either letting sodium in or potassium out, you are bringing the membrane either closer to zero, which would be equilibrium, or further away from zero, which is another case altogether, and we'll get into that in another video. But 70 millivolts is the resting membrane potential. So that is resting membrane potential from front to back, as well as how we measure it. So in the next video, I'm going to explain what happens when you disrupt the resting membrane potential, so when you undo it. In the meantime, thanks for watching, and I'll see you in the next video.